Okay, well, thanks everyone. This has been a fantastic SAG with great organization, and I've been learning a lot with all of the other talks. And so I'll be talking on behalf of our team, which includes Rob Zellem, my co-lead, and a bunch of people who have been fantastic in contributing to this effort. Let me hide my box. Hold on. Sorry, 1 second. There you go. Okay, so our subgroup is SG5. We are tasked with looking at future complementary observations. And specifically, we're tasked with studying possible future complementary observations that could be performed, in order to tackle what the SAG was formed to do, to better quantify and constrain stellar heterogeneities to aid exoplanet transmission spectroscopy studies. And so our goal is to identify facilities and observations that support the critical capabilities needed to tackle the goals of the SAG, which will really be the findings from the other subgroups. So we've heard a lot of the findings from SG1, which is measuring stellar heterogeneities and photospheres and chromospheres, from looking at what can help us with spectral decomposition, and SG3 and 4, which are looking at occulted and unocculted active regions. And also, mixed among these subgroups are models, methods, and data sets. And so all of these are topics that we've been keeping in mind while we tackle our goal. Okay, so what our task is really science-driven, as I just mentioned. So we will be identifying critical capabilities, we meaning this whole SAG21. And so this is really trying to understand what wavelengths, resolution, and timescales, et cetera, are needed for all of these different avenues. And so we will definitely be iterating because we've heard a lot of preliminary results, but there will also be a lot of results that will be revealed in the coming weeks and months that we will, incorporate in our findings. And so what we've done is summarize current and expected facilities and observations and methods. But again, this is a work in progress. And ultimately, we'll be identifying and prioritizing what facilities are needed from, that we don't currently have on the, astrophysics landscape, and, from NASA and ESA and Groundbased and Spacebased platforms, and ultimately provide a recommendation to NASA. So I see this kind of as, what the Astro 2020 Decadal was meant to do for all of astrophysics, but basically focused on this sort of nice task that the subgroup was formed to do, which is one of the gaps in the XEPS science gap list. And we're all familiar with the current astrophysics landscape. So in addition to all of the ground-based observatories, really, when we're trying to find complementary facilities, complementary to what? So we are looking at space-based transmission spectroscopy efforts currently, which we have with Hubble, and in the near future with James Webb, which will launch later this year, and of course Ariel, and there are some others. And I hope I didn't miss circling some, but I just wanted to highlight that, these are these nice missions that we're building to get increasingly precise measurements for studying exoplanet atmospheres. When we try to measure more precise atmospheric features, then all of these, stellar activity sort of contamination problems become more persistent. So I just put this together just to kind of highlight, reiterate where we are right now. On the left is the time scale of, or the timelines for some of these missions. Currently, well, Kepler is done, and K2, but TESS will have an we're in an extended mission right now, and we can continue with this extended mission as long as we have funding for a long time. With Hubble, the goal is to get through 2025, and that can certainly run longer. That would be fantastic if so. And James Webb and Ariel, are on the horizon. And so, what our goal is really to, take this and try to fill in gaps. What other observations are needed to complement these missions. On the right are just kind of a high level look at the wavelength coverage from these missions that are going to be doing space-based transmission spectroscopy. I did it really fast, so I'm not sure the bars for Hubble and James Webb are exactly precise, but really the idea is, while Hubble does have this coverage from 0.8 or whatever to 1.7 micron, they have a bunch of different filters that don't operate simultaneously. So you have to kind of take that into account. And the same with James Webb. All of the James Webb observations will be 0.6 micron and higher. And Ariel will be fantastic when it launches, I believe in 2029 is the current date, which will have a nice broad coverage from 0.5 onwards to 7.8 micron. And I dropped this in. This was made by Nicole Colon, who's the deputy project scientist for exoplanets for James Webb. She put these plots together that basically show all of the planets that are currently on Webb's target list for the Guaranteed Time Observations GTO program and the Early Release Science program. So on the left, this just gives you an idea of, what the exoplanet host stars are like. Whoops, 1 second. It says my Mac is going to fall asleep and I unplugged it by accident. Sorry. Okay, I don't want that to happen. Okay. And so you can see sort of the range of the host star masses go from, as small as tiny TRAPPIST up above 1.5 solar radii. And you can see a lot of the smaller or low mass exoplanets that we're trying to probe with James Webb are orbiting these small stars. And, we saw from the subgroup 1's talk some nice plots about correlating stellar activity with smaller stars. And so this is definitely, whoops. Oh, shoot, sorry. I'm using it. There. Okay, can you see my screen again?
Yeah, we see it.
Okay. I'm using a new laptop because I can't use my NASA laptop. Haven't used it in a while. So you see that a lot of the James Webb targets are going to be around these small stars, and then you can see the distribution in host star temperatures on the right. And so this SAG is definitely a great program that is timely. We really need to resolve these problems of stellar contamination soon. Okay, so questions we're working on is really what ground-based observations do we have and are needed to quantify and mitigate stellar contamination and maximize the results from transmission spectroscopy? What additional space-based observations are needed? We have all these nice, faster, better, cheaper platforms that Thomas Zurbuchen up at NASA has really been pushing, which is great for these types of, sort of focused problems. And then what ground and space-based observations need to be conducted simultaneously? And also what sort of wavelengths and coverage do we need? So I put together these findings. They're kind of obvious findings, but I thought just kind of reiterating, to show that these are topics that we as a subgroup are thinking of. So we have done this exercise of collecting a list of all of the ground-based telescopes, both large and small, and the space-based telescopes, large and small. And so we have this whole, suite of facilities. And really to move forward, looking at what are the recommendations and kind of summarizing what we have and trying to fill in the gaps, we really need an interdisciplinary approach. So this is known. I think we have heliophysicists and astro and planetary scientists on the SAG. There were some really nice white papers by Ben Rackham and Adam Kowalski presented to the Astro Decadal 2020, showing the sort of cross benefits to helio research and stellar research as related to star spots and faculae and what we can learn from both disciplines. And we asked our participants from our subgroup to add in some slides on some ideas or some of the work they're doing, particularly our early career scientists. And so the next 2 slides were put in by Kevin Stevenson from Johns Hopkins. And so he was thinking about sort of what would be useful for kind of doing these proof of concepts for some of the other relevant subgroups. And so validating spectral decomposition methods through observational data is an important first step. And so we know that really the only star that we can spatially resolve is the sun. We did see some fantastic graphics by Rachel Rotten. I don't remember how to say her last name, by Rachel, who has been using interferometry to really resolve spots from some distant stars. And so I love that this whole field, has gone from, taking stars as point sources to really bringing them forward to 3-dimensional objects and being able to break some ground on resolving these is fantastic. But really the sun is what we have right now, which we have the best opportunity to constrain spots and faculae. So Kevin had this nice idea of using existing facilities that provide time-dependent spatially resolved images of the sun's surface to inform spot and faculae fraction and provided ground truth. And sorry, why my pictures keep covering up my text. Okay. And so he had some ideas that CubeSats and SmallSats could spectroscopically observe the sun as a point source and try to validate some of the proposed methods to use spectral decomposition as a method to mitigate stellar contamination. And so this is kind of the same idea of using Earth as an exoplanet, so using sun as another star. And validating models for unocculted active regions can also make use of the spatially resolved information from the sun. Kevin had an idea to use a nearby body like a planet or moon to transit the sun. If you put something at L2 and observed it transit, that could be a nice way to quantify the impact of both unocculted and occulted active regions from this transit. And so these are some nice ideas that I think would make really fantastic CubeSat and SmallSat missions. And let's see. Hold on, I have to figure out, sorry. I don't know how to get rid of these things that keep popping up. Whoops. Okay, well, I'll just
Not blocking any of the text.
Oh, it's not on yours. Okay, so it's just me. I can't see it. Okay, so our preliminary finding 2 that Multi-wavelength observations taken simultaneously in some cases will be needed. We've heard some of this from some of the other talks, but one example is another subgroup recommended, having shorter wavelength spectroscopy complementary to James Webb's observations would be really useful in trying to identify some of the contamination. And we've also heard, simultaneous photometry would be useful. So there are a lot of great ideas. And so our job is to understand what can be done now and what facilities do we need. And so doing these multi-wavelength campaigns can be tricky, even if we have the current facilities and observations. Telescope time is oversubscribed. Trying to get simultaneous observations certainly can be done, and we'll show some examples, but it does take some effort. So where could we use some dedicated balloons or CubeSats or small sats is something that we're looking into. And of course, the multi-wavelength aspect of probing stars in the sun will really help us understand what's going on in the different layers of these stars, and try to understand the underlying physical processes that are generating these active regions. And so we still have a lot to learn, even with the sun, on the origins and what's going on. So we can understand the timescales of changing spots, spatial distributions, and everything else that we've been learning from the other talks. So I just threw up the slide. I didn't want to put our whole list of all of the facilities we've collected, but just kind of to illustrate, there's a large number of small sats and CubeSats already in space. This is NASA's, I think, the most current plot showing all of these measuring aspects of the sun, and then astrophysics is kind of a new, it hasn't been as widely studied as the Earth, but NASA has been putting out more opportunities for that. And so, identifying, which of these would be useful, and also what other ideas could be proposed is something to think about. And, also ground-based facilities. I put this plot in, it's by Jen Burt, who put together the slide of all of the facilities that are helping with TESS's follow-up network. And so I think the blue are photometric facilities, and the red are facilities that can follow up with mass measurements. But sort of, really looking across everything that we have and identifying, what can be useful for the topics for the SAG is an exercise we'll be doing. And as I'll say in the last slide, we will certainly welcome feedback from the community and from the other subgroups. Okay, so we have a couple slides from some of our participants. This is by Sarah Casewell, who unfortunately can't make it because of the time zone, but it's just to highlight some of the current facilities that we have. Next Generation Transit Survey is located at Paranal. It's an array of telescopes, and they are observing, from around 520 to 890 nanometers. This is a fantastic resource that will be definitely useful for our efforts. And the data will be available from the ESO archive about a year after observations. And this shows some nice data of some of the flares that they can observe. And Speculoos, we have Elisa. Did you want to?
Yeah, I can talk about it if you want. So okay. I'm going to put my video on. Hi everybody, I'm Elsa. I'm just going to present this short slide on Speculoos. Just everybody heard of it, but we have a network of 6 telescopes and at different locations in the world. So in Chile, in Mexico, and in the Canary Islands. And what is nice is that we can do indeed simultaneous photometry. And you see on the right this plot by Murray et al. 2020, when we see the capability of the SS observatory compared to TESS, so we can reach a great precision in terms of photometry and access several filters. So I guess it could be quite useful to second the effort here in this working group. And also, I forgot to mention, but as NGTS that are public on the EDO archive 1 year after being taken. So yeah, that's pretty much it. It was just a few words about Speculoos. Thank you, Elisa.
Yeah, thank you. Yeah, this is fantastic. And this is some work done by some scientists at Goddard, NASA Goddard, and collaborators that we thought was relevant. And so this is a project to study M-dwarf flares through time. And this is a project that involves heliophysicists and astrophysicists working together. One of the nice things, really starting from the Kepler era, is that we now have this long baseline photometry that can give us one axis of what's happening with this stellar activity. And really, if there were a lot of really nice studies pre-Kepler, by Rachel Austin and her group and some other groups looking at trying to line up flares from different facilities. It wasn't really until we have Kepler and now TESS where we can get many, many flares from single stars. And for TESS will be observing hundreds of thousands of M-dwarfs, so orders of magnitude more than Kepler and K2. And this has really opened this new era in stellar activity research. And so the idea—
warning, Elisa.
What's up?
2-minute warning.
Oh, okay. Yeah, so this is an effort where we have a multi-wavelength campaign to obtain SWIFT and UV data from Hubble, radio, all simultaneously with TESS. And TESS has this new fantastic mode of 20-second cadence data that can really resolve these flares. And so trying to understand this activity from a bunch of different wavelengths is a fantastic effort that I think will shed light on a lot of unsolved problems. And this is also obvious. Improved observational constraints will yield better star and planet models. I just wanted to reiterate that this is something that we are thinking about, and also what is sufficient? How better resolution do we need, both in space and time? This is a few future modeling and direction needs that this was provided by Aisha Iyer, sorry, basically to show that we will require accurate precision modeling of star spots, flares, and prominences. She's doing some fantastic work. Oh, I'm sorry. This one is by, sorry. This one is by Sarah Peacock, who's working on sparks and UV scope to put together some really nice models. And what is really needed is a lot of UV and shorter wavelength observations to better enhance her models. And these are from Aisha. There's this 2 more slides that basically shows that bias and retrieve planet properties, despite TL transit light source correction, can happen if you don't have accurate stellar models. And so it's really getting our models right, which means getting better observations. And I'll post these slides so people can look into it more. And I encourage you to talk to Aisha. She has some really fantastic research going on. And that's it. Yeah.
Wonderful. Thank you, Elisa. So again, remember to post questions in the Slido. So our first question is, you discussed observations of planet transits from L2, and this anonymous person is curious about what the advantage is of those observations versus using high resolution solar images and modeling transits.
Yeah, so I think this is work done by Kevin Stevenson and a group at APL. And I think Laura Mayorga is going to be giving a talk later today that might answer some of these questions. But I mean, thinking about the Earth as an exoplanet case, we do have tons and tons of observations from low Earth orbit. And I know going out to L2, like the Discover observations, you can get more phase coverage and look at it more as a distant object, and which is more aligned with what we'll be seeing with other exoplanets. So I think that's the idea. But Laura can talk a little bit more about this, I think, or we can ask Kevin, when, or you can.
Laura
ask
has
Kevin.
posted in the chat that yes, indeed, she will be discussing this in her talk. this
Okay,
afternoon.
fantastic. Yeah, but I think it's a sun as a distant star would be what I think.
I know we have a question from Leonardo that sounds very hard. What are the prospects for organizing a centralized network for facilitating ground and space-based observations?
So that's an excellent question. So the prospects of combining these two. So I know so Rob Zellem has been working on citizen science campaign to connect ground-based facilities. There's a test follow-up network. There's CELT network that does, all these do fantastic jobs at organizing ground-based efforts. Connecting that with space-based efforts, I think, is something we can all do better at. And maybe that's something we can look into when putting together this report. That I don't know of any strong programs that do such a thing. If anyone online, has some input, feel free to speak up. But perhaps this is something that we, could look into if it's something that we can think of some feasible ways to do it and make some recommendations. I think that's a fantastic idea.
Okay, Ben has a question. Has the subgroup 5 discussed ways that we could leverage high resolution spectra from RV studies to help probe photospheric heterogeneity of exoplanet host stars?
I believe so. What we've done is basically brainstorm, and we have a lot of information, and we're kind of going through the funneling portion, which will require input just as this one in what is needed. So I don't recall if we specifically have that, but I think that's definitely some useful information that that we can put into our funnel as we try to identify what we have and what gaps there are. So is this Ben Monte or a different Ben? So
This is Ben Rackham.
Ben Rackham, okay. Yeah, so
I should know, but I don't.
I mean, I believe so, because Rob Zellem is sort of our observation lead, because he's more of an observer than I am. So I think he's brainstormed a bunch of stuff, but I'll have to look at that specifically, but we'll certainly take that input.
All right, excellent. Thank you, Elisa. And thank you again to all of our speakers from this session.